Talofa lava, and welcome to our next video on how to make alcohols, and then I'm going to talk about the reactions that alcohols have. Some of those reactions you should be able to remember, some of them will be new. Same with how to make alcohols, you should be able to remember this from last year. So let's get going. How to make alcohols. Alcohols can be made by nucleophilic. Here's a cool new word for you, nucleophilic, but you'll know these reactions as substitution reactions. So we substitute OH minus onto something from X minus. So chloride or bromide or iodide on haloalkanes. It's one way we can do this. So substitution. If you're interested, you can go look up what a nucleophile means. A nucleophile is something, well, as far as we're concerned, a nucleophile is something that has a negative charge that can come in and attack. Okay, or we can make an alcohol by addition of water to alkenes. Remembering that if you do addition of water to alkenes, then you will have minor products and major products due to Markovnikov. Or, another way to make alcohols is reduction. Now, this is something that you might not be familiar with. So this is something you might need to do a little bit more look in. There's some nice pages in your books which you can probably look up for this. So reduction of aldehydes and carboxylic acids so they will make primary alcohols, and ketones to make secondary alcohols. The reagent is used as sodium borohydride, NaBH4, or lithium aluminium hydride, LiAlH4. This, you kind of got to think you should probably really be aware of oxidation of alcohols to make carboxylic acids. So there's no reason if I have oxidation going in that direction that I could have reduction going in the backwards direction. Right. So we'll move on to reactions of alcohols. So I could have an alcohol and I could do an elimination reaction or dehydration reaction to form an alkene in water. Now dehydration simply means if you are dehydrated, you are lacking water. So dehydration is we are removing water from an alcohol. So removing the OH and a hydrogen to make an alkene and water. Now a little bit of interesting aside here. I'm going to put my little pen here. We're going to get my pen out. Here we go. This reagent here, concentrated sulfuric acid, this is known as a dehydration reagent. Whenever you have a reaction that requires you to remove water from something, this is your best bet. So if you get one of those lovely reaction schemes, which everybody loves to do, not really, then you will probably be best to remember that dehydration requires concentrated sulfuric acid and generally heat. Now, the little aside to remember here is this elimination reaction has what is fondly referred to as anti-Markovnikov, which just always makes me laugh. Markovnikov, depending on how you want to spell it. Now you'll remember that Markovnikov's rule is to do with addition reactions, and we say that the rich get richer. Yeah, that is how you remember it. That is not how you write it down in the exam. You could write the rich get richer, but that will get you nothing. Nada, zilch, zippo, nothing. So you can write it down, but then you must explain what you mean by it. So of course what you mean by the rich get richer is that the carbon with the most hydrogens will get that hydrogen when you add H and something else asymmetrically on to make the major product, and if the other way around will be the minor product. So this here is going to be an anti-Markovnikov. Now I've given you a nice example in this one here, propane-2-ol, which is symmetrical. So it doesn't matter if I take one of those hydrogens or one of those hydrogens, I'm always going to end up with prop-1N. Okay, but if I have butane-2-ol, okay, I could take the blue hydrogen, or I could take the red hydrogen. Yeah, so I could take OH and H and make a double bond here, or I could take OH and H and make a double bond here. So I could make two products. I could make C, 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 tasty like these. No, this is H. Could make 1, 2, 3, double bond C, 1, 2, 1, 1, 2, 1, 2, 3, or I could make C, C, tasty like these, C, C, 1, 2, 3, 1, 1, 1, 2, 3. Yep, that's right. Cool. I can make but-1N or but-2N. Okay, depending on whether I take this one to make but-1N, this one to make but-2N. So, anti-Markovnikov. Anti-Markovnikov means the poor get poorer, is what anti-Markovnikov. So instead of the rich get richer, here we go, the poor get poorer. Everyone go, oh, that's so sad. Not really. So, the carbon with the least number of hydrogens, which in this case is this one with the blue hydrogen on it, that one is going to get poorer more often than this one that already has two other hydrogens, 3 hydrogens total, 2 hydrogens total. This one is going to be known as the rich. It's hydrogen rich. This one is hydrogen poor. So this one's going to get poorer, so therefore this will be the major product, and this will be the minor product. Okay, so this poor, well, no, carbon is poor. So that one's going to come off more than that one. Okay, anti-Markovnikov. Weird. Right. Then we could have reactions of alcohol. So we have a substitution reaction. So we can substitute the OH minus by a Cl minus to form a chloroalkane. Interestingly enough, this substitution is faster for tertiary alcohols than secondary, and secondary is faster than primary. We might do a reaction in class. We could do this. I can show you. Okay, so substitution reactions we could do is PCl3, PCl5, SOCl2, so phosphorus pentachloride, phosphorus trichloride, and thiochloride. You got to remember, these will go. It's an easy way to determine the difference between tertiary, secondary, and primary alcohols, is how fast they will react to a substitution reaction. Tertiary is fast, secondary slow, primary so slow. You might see, I've got written this down the bottom, you might see that some books will refer to a Lucas reagent, and if you want to, you still can refer to a Lucas reagent, which is zinc chloride and concentrated hydrochloric acid, but that's not included in this achievement standard from pretty much last year. Year before that, when the standard changed, 2013, it's not used anymore. So you might see books that will still talk about Lucas reagent, and it still exists and it's still a valid thing, but it's just not, we don't have to teach it. It's still true. Right. More reactions. So number C here is oxidation of alcohols. You should be okay with this. You should know this. Oxidation of alcohols is something you should be able to refer to. However, we're going to change it slightly this year, because the type of product formed depends on whether the alcohol used in the oxidation reaction is primary or secondary. So you would have known that primary alcohols go to make carboxylic acids. Yeah? That's what you know. Ethanol goes to make ethanoic acid. However, I'm going to freak you out slightly, because you know that ethanol will go to ethanoic acid, but you probably didn't know there is a there's a step in between there where you oxidize ethanol to ethanal, and then ethanal will oxidize to ethanoic acid. If you think about it, it kind of makes sense. Yeah? You oxidize the oxygen to form the double bond, O, and then you just have a hydrogen. And then you have another oxygen, OH, that will come in and oxidize that. Okay? Because potassium dichromate and potassium permanganate are known as strong oxidizing agents, then this will generally go straight through to ethanoic acid. It will pass through the ethanol stage, but it goes so freaking quickly that you can't even tell. Okay? This is true for all primary alcohols. So what do you think is going to happen if I have a secondary alcohol? That's right, secondary alcohols will go to make ketones. Okay, you think if I oxidize this part here, I'm going to end up with a double bond there, and that's what happens. So secondary alcohols are oxidized to ketones. Cool. Tertiary alcohols do not react with oxidizing agents. They just don't. Okay, so oxidation reactions can also be used to distinguish tertiary alcohols from primary and secondary. But of course you can't really tell the difference very easily between the primary and secondary alcohols. Yeah? If I mix potassium permanganate with a primary alcohol, it will go from purple to colourless. If I mix potassium permanganate with secondary alcohol, it will go from purple to colourless. If I mix potassium permanganate with a tertiary alcohol, it'll stay purple. Okay? Alright. Here's a question for you to have a go at. Ion electron method. Write balanced equations for the following redox reactions. Use structural formula for the organic molecules. Okay, so there's the oxidation of propane 1-ol to propanal, so that's your aldehyde, by acidified potassium dichromate. Oxidation of propane 1-ol to propanoic acid by acidified potassium permanganate. Oxidation of butane 2-ol to butanol using either oxidation reaction. I'm just going to check. That's it though. You're done. You can show those to me in class, or if you are stuck doing those, come and talk to me in class and I will help you to get started. Okay, I will see you next time for, I don't know, we'll see.